Hello everyone. In the tutorial we are going to talk about cloud native application architecture and some of the fundamental concepts around the cloud native application. Now, why do we need cloud native application? The demand for today's modern day application is such that it can be met by cloud native application architecture or the concepts which are there in the cloud native application architecture. That is why we need to go through first what are the needs of the modern day application. So we'll start with some of the fundamental concepts around microservices and modern day application. Then we will move over to what exactly is a cloud native application, which are the technologies driving development of cloud native application. Now before we get into details, let's look into what exactly we are going to cover. So to understand the cloud native application, it is extremely important to understand the fundamentals of the microservice. I'm assuming that most of us would be knowing some things around the microservices, but still we'll go over some of the basic fundamentals of the microservices in this tutorial as well. Then, as I said, modern day application. What are the demands or the needs of the modern day application? Because unless we understand what are the needs, we won't be able to appreciate the cloud native application architecture and concepts. So that is why we'll go over what are the needs of the modern day application. Then we'll move to a definition of the cloud native application, architecture concepts around the cloud native application. Then again, we'll see what are the attributes of the cloud native application. Then we'll move over again back to the microservice. We'll try to understand how the microservices communicate with each other. The microservice as a container communicate with each other with the help of the orchestrator. Now, what is this orchestrator? We'll see what this orchestrator we are talking about here. Then we'll again go back to cloud native technologies, that is technologies which are driving this cloud native application development. As we would be knowing by this time that the Kubernetes has become a de facto for cloud native application development. So we'll see what is Kubernetes and then some of the terminologies in the Kubernetes. So this is how we'll go over this tutorial, and I hope you will find this interesting. Now, to understand the concept of the cloud native application further, let's look into what the microservices are, because microservices are the basic or the fundamental building blocks of any distributed application nowadays, which is classified as the cloud native application. So let's revisit microservices. Now in this, what we are showing is an e-commerce application which has got account service, product catalog service, cart service, order service. That's what you can see over here. Now these are in a monolith application, these are simple functions which collaborate with each other to form an application. So these are the functions. Each of them are small functions within an application, and they collaborate with each other to form a bigger application. Now each function here qualifies as a separate service running as independent unit in the microservices world. Now these are different processes in the microservices world. That is, account service is a separate process, product catalog service is a separate process, likewise cart service and the order service. These are different processes. They are running in different runtime environments, and then they collaborate with each other to form a bigger application, in this case an online e-commerce application. So how do we define the microservice now? A microservice is a small independent service that performs a specific function within a larger application. Like here, account service performs all the things related to the account. Product catalog, probably it stores a product catalog. Cart service, you put the things into the cart, that is what it does. It helps in doing that. Order service is helping in taking the orders. So each of these services are doing some independent job, that is independent task. Now each of these services communicate with each other via APIs. That is, account service can communicate with product catalog service via API, and cart service with order service or with any other service via the API. And important thing to note over here is that each of these service can be developed, deployed, and scaled separately. This architecture improves flexibility, scalability, maintainability, and offers a lot of advantages that we'll see as we move to more details about the cloud native application. Okay, now let's see how a modern day application look like. That is, what are the challenges in the modern day application that makes us to use cloud native application development approach. So let's go ahead with this. Modern day applications, as you know, is distributed and complex. The landscape of distributed application is quite complex, and customer expects continuous availability and unparalleled responsiveness with innovative solution. So this is the requirement. Like, you take any e-commerce application or any other application today, banking application, financial application, or any supply chain management application, all of them should be available around the clock. They are distributed in nature and complex. Distributed nature of the application makes it complex. This is one. The other one is as you know, the customer expectations, whether it is e-com business or any other business, or in fact, the CRM, anything you take, the expectations by the customer is very high. Customers have greater expectation, and the business can grow only if its system exhibits certain attributes. Disruptions in service can lead to business losses, and hence cloud native have become the need of the hour. Then there is no downtime. As I said, the application should be available 24/7, 365 days, and there should not be any downtime, even if you are upgrading or fixing any issues in your system. Then support business growth. That is, any application that you have, it should also support business growth. Unless it supports, you cannot grow in future. So that's one of the prime requirement of the modern day application. Take any application again. The application has to be independent. That is, application design principle should make independent development and deployment feasible, which ideally is in line with the agile methodology. That is, if you have bigger application and if you go with microservices, each of the service should be independent. That is how the development should take place. Then obviously the security is one of the major concerns today with the cloud and all, and this has to be taken care of by the application. Or even if you deploy it on the cloud, then cloud infrastructure or the cloud services, managed services should be able to address these concerns. That is, concerns around the security. Now that we have seen what are the requirements or the needs of the modern day application, let's see how we can solve this. That is, how can we overcome the challenges? That is, how can we make the application which is can withstand the requirements of the modern day application needs. So let's go ahead and look into that. But even before going to how to solve the requirements or the needs or the challenges of the modern day application, let's see what a cloud native application approach offers us, and we'll see after that if cloud native application can really solve our problem or can really overcome the challenges of the modern day application. So let's look at what the cloud native application offers. Cloud native applications are scalable. That is, the application can scale up with increase in the workload or traffic, designed to scale with growth. That is one of the important attributes of the cloud native application. Then resiliency. That is, it has to be resilient, withstanding any disruptions. It can be in the form of some components failing or complete cloud region going down due to some disasters. But your application has to keep running, and it has to be resilient to any such failures or any such disruptions. No downtime. Again, the cloud native application, they do not have any downtime. Ideally, they do not have any downtime, but there can be certain instances where there is a downtime. But most of the time it has to be up and running. That is one of the attributes of the cloud native application. It has to be elastic. Again, it has to be as I said, scalable. With the increase in the load, cloud infra should be able to increase or decrease the instances
serving the request. So scalability is the requirement. Now to scale, you need extra hardware or extra, the infrastructure. So the wherever you deploy, it should be able to increase the infra or the hardware as per the needs. That is what is called as elastic or elasticity. Now again, it has to be secured. The cloud native applications are secured because they are leveraging all the features from the cloud itself. Then independent, the architecture of the cloud native application is such that each of the services within the application are independent to each other, and they are developed, deployed independently. They have their own development life cycle. That's what makes all the services within the application independent. So these are the attributes, or these are some of the attributes which comes out of the cloud native application way of development, I would say. That is, if you develop the application as per the guidelines from the cloud native approach, then you can achieve all these things. So let's look at one of the important attributes of the cloud native application, which is scalability. We'll see this how it works with the help of an example. Okay, let's consider an application which is an e-commerce application. Again, and I'm taking the same example of e-commerce application. Now the application can scale up with increase in the workload or the traffic. It is designed to scale with the growth, that is the business growth. Now let's see how it scales. So what you see over here is a time and the transaction per second graph. Now on the x-axis what you see is the time, and on the y-axis what you see is the transactions per second. So with the time, the transaction per second is increasing. So on the usual day, the request to the e-commerce application can be served with one instance of the application, say at 3 p.m. That is, at 3 p.m. what you see, the order service is just one instance. Now with the time, let's say at the 5 p.m. the traffic increases to 125 TPS. That is what we see on the x-axis. What you see over here, the 5 p.m. the traffic has increased up to 125 transactions per second. So to serve the increased traffic, we need one more instance, and hence what we see over here is that we are seeing two instances of the order service. That is what you see over here. Now again at 8 p.m. if you see, the traffic increases to 250 TPS, that is double of 125 TPS. Now to serve the 250 TPS, we need more instances of the order service. Hence we have increased the number of instances to 5 over here. Now this is what the scalability is, and with the help of the elastic nature of the cloud infrastructure, it is very easy to scale the number of instances of this order service. Now again at 9 p.m. the traffic decreases to 200 TPS. That is, at 8 p.m. it was 250, and at 9 p.m. it is again gone down to 200 TPS. So we would need only 4 instances of the order service, and that is what is shown over here. So what we are saying is that the application should be able to scale instantly when the traffic increases, or the number of instances of the application should decrease as the traffic decreases. So this is called scalability, and it is achieved with the elastic nature of the hardware that is offered by the cloud services. Now if you see, we are saving a cost on the hardware, because unless we need the lot of hardware, we just provision only a small portion of the hardware, and as the traffic increases, we increase the hardware, and hence we also save on the cost. So this is an example showing how scalability can be achieved with the cloud native application. And this is, as we saw, the scalability is one of the most important requirement of any modern day application. Now let's look at another important attribute or another feature of the cloud native application, which is resiliency. Now we'll try to understand this with the help of an example over here. Again, we are taking an example of the e-commerce application, which is consisting of multiple services. Now here what we see is the order service, cart service, account service. Order service is making call to the cart service, and cart service is making call to the account service. Now what you see over here is an orchestrator. Now we are going to discuss what this orchestrator is in subsequent slides, but for now assume that this is something which is facilitating the communication across these services, that is from order service to cart service and to the account service. Now under normal circumstances, under normal scenario, a request is fulfilled by a series of microservices interacting with each other. That is what we see over here. Now if one of the services in an application goes down, then the rest of the app services within an application should still be functional and should be able to respond back to the user in an appropriate way with the appropriate message. That is what the resiliency is. Now ability to react to failure and remain functional is resiliency. That is what we said just now. An e-commerce application will have multiple services. That is what we see over here, and failure in any service should keep the e-commerce site functional and it should be able to respond with appropriate message. In this case, account service used by this e-commerce application, if it goes down, the e-commerce application should be able to gracefully handle it and show appropriate message to the user. This is a user request. It is coming first to the order service and to the cart service, but cart service sees that the account service is down for some reason. But still this entire application should be able to handle this request and show appropriate message to the users. This is what is called as resiliency. It is resilient to any failures as such. Now let's quickly revisit cloud native application, what it offers. First is scalability, resiliency, no downtime or minimal downtime, elasticity, highest level of security, and independent development of the services. Now we'll see how this is possible, that is how it is possible to achieve all these things in case of the cloud native application. So let's go over to the slide where we have covered all these things. Okay, so cloud native application attributes, that is we are going to see how it is feasible to achieve all the features that we saw just now for the cloud native application. Now those features are feasible or it's possible because cloud native application uses cloud. Now moment we say that it uses cloud, there are a lot of features which comes out like scalability, elasticity, and the security. All such things comes along with the use of the cloud infrastructure. Google Cloud Services, AWS, Azure are some of the prominent player in this area where we can deploy our services. Now we also follow agile methodologies for the cloud native application development, because we know that the cloud native application consists of multiple microservices and it is feasible to do the development of the independent microservices if we go with the agile methodologies. The life cycle of each of these services are independent to each other, and that is how it makes it possible to do the independent development. Now again, microservices are important part of the cloud native application, where each application is made of a multiple microservices, and these microservices can again be deployed on the cloud infrastructure. Now these, as we said, the applications are consist of multiple microservices. We need something which can orchestrate or manage the call across these microservices. That is what the orchestrator does. We are going to cover the details of orchestrator in the next subsequent slides. Cloud deployment, because we are using cloud and the microservices, we use the cloud deployments for microservices deployment to the cloud infrastructure. As I said earlier, the microservices are loosely coupled, and that's what make it resilient, or the application is resilient, and then development is independent. Development of each of the microservices are independent, and this is one of the requirement of the cloud native application. Now again, any application that you develop, we are able to deploy to multiple uh, clouds. That is, we can deploy the same application to AWS, same application to Google, same application to the Azure. So this is feasible. However, there would be some changes if you are using managed services from these clouds. Otherwise, if you are using uh, microservices which are agnostic to the cloud, then we should be able to deploy our application across all the different cloud providers.
Okay, to understand the cloud native application better, or to understand how modern day application can be built using the cloud native approach or architecture, let's revisit the microservices once again. So let's revisit what is microservice architecture to understand how each service communicate with each other and how can distributed microservice based application be deployed as cloud native application. So to understand this, it's important to see how microservices applications work, or rather, in an application, if there are multiple microservices, how do they communicate with each other? So here again, it's an example of e-commerce application which is built using different microservices like account service, product catalog, cart service, order service. Now, how do these services collaborate? For this, we need some additional piece of software which can orchestrate calls across these services. That is, account service, product catalog, cart service, order service. We need some piece of software which can orchestrate or manage the calls across these microservices. So that is what we are saying here. As an example, account service may have to make call to product services to get cost of product selected by user in an e-commerce application. Now further to this, what we are saying is, as an example, account service may have to make a call to product service to get the cost of the product selected by the users in the e-commerce application. Here, an orchestrator is responsible for orchestrating services like account, product service by managing deployment, scaling, and self-healing. Now, it uses DNS for automatic service discovery, allowing microservices to communicate seamlessly without worrying about changing IPs. Now let's see how the orchestrator helps to achieve this. Now let's try to understand this further by taking an example of account service communicating with the product services. Now we have an e-commerce application where account service and product service are two microservices, and let's see how an orchestrator helps to communicate across these services. Now an external client sends an HTTP request to the account service. That is, this is external client sending a request to the account service. The account service processes the request and determines it needs to fetch product information for the user. So it determines that it has to make a call to the product service to get the product information. So to do that, the account service resolves the DNS name of the product service to cluster IP of the product service using Kubernetes DNS. That is, DNS is where it has got the address of all the microservices within the service orchestrator or within the cluster. So account service first has to get the address of the product services from core DNS, which is part of the Kubernetes itself. So as a first step, this is what it is doing. The account service makes an HTTP request to the resolved cluster IP of the product services. That is, account service, once it gets the cluster IP of the product services, it then makes a REST call to the product services. The product services processes the request and returns the product information back to the account service. The account service combines the user and product information and sends a response back to the
external client. Now this is how the services within the cluster work, and the service orchestrator is the one which helps to achieve this. Now that we have revisited the microservices based application and also seen as how the microservices communicate with each other within a cluster, or how a service orchestrator helps to manage the communication across these microservices within an application. Now the next question is, what are the technologies which empower cloud native application development? That is what we saw: the microservices, the communication across the microservices, and the service orchestrator that we saw. Now to achieve all those things, what are the technologies? So let's see that. Kubernetes, Docker, serverless functions are empowering cloud native application development. These services provide way to focus more on application development, reduce operational tasks for the developer. But let's see how. How do they help? Let's see if Kubernetes provides a way to develop a scalable, elastic, resilient, and highly secured cloud native application. These are focused on increasing developer productivity as well. So we are going to look into Kubernetes, like whatever attributes or the properties of the cloud native application that we saw so far. We will see if Kubernetes really helps to achieve all those things, including the service orchestration, that is microservice orchestration. Okay, now let's see what Kubernetes can do. Many orchestration frameworks begin to appear when microservices based architecture evolved. That is, when microservices based architecture were evolving, there were many orchestration services which also evolved. However, it was not long before Kubernetes became the de facto standard for orchestration. So what we saw as an orchestrator service, Kubernetes is one of them. These days, it would be unusual to find a cloud provider that doesn't offer the ability to deploy application into Kubernetes. Google, Amazon, Microsoft all offer Kubernetes as an orchestrator. Yes, obviously with some kind of customization on top of the open source Kubernetes. For developers deploying application to a hybrid cloud, it makes sense to shift focus from cloud native to Kubernetes native. That is, Kubernetes native has become synonymous with cloud native because all the features Kubernetes offers. That we'll see in details in the upcoming slides. The key takeaway is that Kubernetes native is a specialization of cloud native and not diverse from what cloud native defines. So this is what the gist is, and we'll go into details of Kubernetes and different technologies supporting the Kubernetes itself. Now let's see what Kubernetes is, as Kubernetes has become de facto for cloud native apps which are using microservices. Kubernetes helps to build cloud native microservices based apps. It is an open source system to deploy, scale, and manage containerized application anywhere. It supports containerization of apps and acts as an orchestrator engine. That is what we saw earlier in the slide. What is an orchestration engine? So Kubernetes acts as an orchestration engine. Kubernetes has become a de facto for distributed application service deployment, again, which are based on microservices. Kubernetes offers scalability, elasticity, resiliency, and high level of security when used as a service on cloud service providers such as Google Cloud, Azure Cloud, or Amazon Web Services. Now, this is what we saw when we started with this tutorial, that the resiliency, elasticity, scalability, high security are the needs of the modern day application, and that can be met by building a cloud native application. And again, the Kubernetes helps to build the cloud native application. So this is what we are saying over here. So these are all related things. Kubernetes helps to build cloud native microservice based apps, is an open source. Kubernetes is a container management technology developed in Google Lab to manage containerized application in different kind of environments such as physical, virtual, and cloud infrastructure. It's an open source system which helps in creating and managing containerization of application. Now we'll see what is container now. Don't get confused with the term containerization or container as such here. We will see what the Docker is and how the running instance of Docker is called as container. And those are managed by the Kubernetes in the upcoming slides. Now let's see what the Docker is. As we can see, Docker is a container engine that enables applications to be packaged into lightweight portable container, making them scalable and cloud native ready. That is, if you have a microservice, let's say written in Java, then this microservice can be packaged into lightweight portable containers using the Docker engine. That is, using Docker, you can package it into a lightweight portable containers, which makes them scalable and cloud ready. That we'll see in the next set of slides as what it actually means. So Docker helps in creating, that is out of the microservice that you might have written in Java or any other language. It helps in creating, deploying and running applications. It enables to package applications with all the dependencies and distribute them as an individual bundles. That is, it is self-sufficient. It has got everything that is needed to run an application. For example, if you have written an application, if you have written a microservice in Java, let's say using the Spring Boot framework, then that can be packaged into a Docker file, a Docker image. That's what we say it as, Docker image, which is self-sufficient. It is independent, and this Docker has got all the Java runtime, that is a JVM plus all the dependencies which your microservice needs to run. So it is really independent and it can be deployed to any Kubernetes cluster. That is what the Docker is. And the runtime instance of this Docker is known as container. That's what we'll see next in upcoming slides. So what we saw just now was about the Docker engine or the Docker plugin, which can be used to build an Docker image or to run the Docker image as a container. Now we'll see what the Docker image is. The Docker image is nothing but a file. It's a bundle. It's a bundle which contains all the information about the microservices itself, all the information or all the tools or the virtual machines which are needed to run that Docker as an independent microservice. So it is a lightweight, standalone and executable package that contains application code and all the dependencies. In other words, we could say that Docker image is like a Java class. And now I'm saying like a Java class, it's not the complete Java class, as we'll see. Assume a hello world microservices in Java. What all it needs to run this microservice are contained in a Docker image file itself. And a container is one instance of this Docker image. So a container has an ID associated with it, right? So you have a Docker image, and when we talk about runtime part of it, then we call it as container. So for Docker image, for Java based application should have operating system layer, that is an image itself should have an operating system layer itself, a JVM, and in our hello world microservices and hello world Java class would need all the jars on which it is dependent. So everything is bundled together in this Docker image. So this is completely independent bundle package which can run independently. That is what is Docker image. So let's see what the container is. Now as we saw that container is just one instance of the Docker image itself, that is one runtime instance. When you run the Docker image on the Docker engine, then it becomes a container. So it's a runtime instance of the Docker image. Now let's look into some other terminologies like pod, which is again one of the important terminology. The pods are the smallest, most basic deployable object in Kubernetes. That's the smallest building block. A pod represents a single instance of running process in the cluster. Now important here is that pods contains one or more container.
Now when you say pod contains one or more containers, that is the runtime instance of the Docker itself is part of the pod. Pod contains one or more containers such as Docker containers, right? So we saw Docker images, and when it runs it becomes a container, and pod is something which is having containers inside it. When a pod runs multiple containers, a pod can also have a multiple containers. The containers are managed as a single entity and share the pod's resources like network, storage, and everything. Right? So a pod can have multiple containers, and these containers share the network resources, storage. That is how it is managed as a pod. Now don't worry if you do not understand much out of this. We'll see more detail about the containers, pod, service, Docker, and the Kubernetes itself. We'll see in a diagram as such, which will help you to understand this further. Now service, again, a service can be defined as a logical set of pods. Now pod is a physical entity, and if you assign some IP to the pods and if it gets destroyed, then IP would change. So there has to be some logical wrapper around it. So that is what is called as service. Now it can be defined as an abstraction. As I said, it is an logical entity. So it can be defined as an abstraction on the top of the pods, which provides a single IP address and DNS name by which pods can be accessed. With the service, it is easy to manage load balancing configuration. It helps pods to scale very easily. We'll see further details about this service with the help of a diagram. Now let's see how the service in the Kubernetes environment looks like. So as I said that the service is an abstraction. It's a logical entity, right? So what you see here, order service as an abstraction. This is an abstraction service, and it can have multiple pods. That is, which can be running Docker container of the order service itself. Like this one is one ordered Docker container. This is second one. This is the third order Docker container, and there is a pod. Now this is deployed. The pod is deployed. Pod 1, pod 2, pod 3 of the same microservice called as order microservice is deployed in the Kubernetes cluster. Now if we deploy individual pod, this will have different IP addresses. Now if some other service wants to access these pods, and if one of the pods goes down, then it will be difficult for the other service to access this. That is why a logical abstraction is created in the Kubernetes, which is called as service, and that is what we see over here in case of the order service. So let's see, a service is an abstraction that represents a set of logical pods. So here order service is representing set of logical pods like this pod, this pod, this pod of the order microservice. The actual pods are ephemeral, that is, it can be destroyed. Kubernetes guarantees the availability of pods and replicas is specified, but not the liveness of each individual pods, right? So if you have 3 pods in this case and one of the pod goes down, Kubernetes ensures that another pod of order microservice is spin up immediately if the number of replicas defined earlier was 3. That is where the Kubernetes helps here, right? So this is the relation between the service, pod, and the Docker container in the Kubernetes environment. Now this is another picture which shows Kubernetes cluster. That is what you see over here. This is in Kubernetes cluster, and you have 2 nodes, the virtual machine node, this first one, and the virtual machine node 2. Now in this, since it's a cluster, so you can have a multiple instance of the given service. Like for example, order service, if I have declared that it should be running always running 2 pods, then 2 pods will always be running over here.
and this will be managed by the Kubernetes orchestrator or the Kubernetes service over here. Now, if one of the pod of the order service goes down, Kubernetes engine ensures that another pod is spin up immediately. But then the IP of this pod will always change. That is, if there is a new pod coming up, new pod has been spawned, then IP of that pod will change. But the outside microservice like card service should always look into the order service DNS name and not the IP. That is where the service helps. And this service, when some request hits this service like order service, it load balances the request. That is, it passes the request to either to this first pod or to the second pod, depending on how the load is on the current pod. That is where the service helps, and the Kubernetes helps in managing all these things. So in this diagram we have shown Kubernetes cluster, then you have two VMs, this VM and this VM. Now if one of this VM goes down, the services are also available on the another node. So it ensures that application is always available, and then that is how it helps to build an cloud native application. Likewise, the card service, if you see, card service can be seen in the node 1 and the node 2 as well. Now if the pod, one of the pod of the card service in first node, let's say, goes down, Kubernetes ensures that it spins up another pod here in the node 1, that is card service of the node 1, the first node. Hence the count always remains 2, so that the load is equally balanced across these two pods of the card service. Now if one of the node it goes down, the second node is always available, and that is how any external request coming to card service will be handled via the second node. And these all things are managed by the Kubernetes itself. So what we are seeing over here is that all the requirements that we saw for the modern day application and all that is fulfilled by cloud native application is also fulfilled by this Kubernetes, and this is how we develop an cloud native application. Specifically, I would say the microservices based application, distributed applications. Now this is the bigger picture showcasing everything deployed in Kubernetes, the microservices in the Kubernetes world itself. Now this is a different example of the service, but as you see, this is in Kubernetes service, Kubernetes cluster, and you can have multiple microservices. Like in this example, we are seeing employee service, department service, security service, all the backend services that you would have is deployed in the Kubernetes cluster itself. Then there is, the Kubernetes also offers some level of monitoring, traces, and the logging itself, especially when it comes to the managed Kubernetes service, like what is available on the Google Cloud or Azure or AWS. Now what we have seen so far is that the basic building block, that is microservices, and then microservices getting converted into the Docker images, and the Docker to the containers and the pods, and then service. All these things, we see that if we build our application using this, then we can fulfill the requirements of the cloud native application. And when we say that it is a cloud native application, we are mostly meeting the requirements of any modern day application that we saw at the start. So this is how a modern day application is built using the principles or the architecture of the cloud native application. Now in upcoming tutorials, we'll see some of the other technologies like Dapr, how it helps to further help in building cloud native application. Now Dapr is the latest technology stack which takes care of the networking concerns within the Kubernetes cluster, also application concerns in the development of microservices based application, and that we'll see in the subsequent tutorials. Thank you so much for watching this. If you have any questions, any queries, do write to me in the comments box. Thank you.